I didn't begin with the theory about lost civilizations. I began with measurements in architectural archives, municipal blueprints from the 1870s, sewer cross-sections from the 1880s, foundation diagrams from civic buildings that still stand today. At first glance, everything appeared consistent with the official narrative of industrial expansion and gradual technological progress. But the longer I examined the physical record, the more something felt misaligned. Not dramatic, not sensational, just subtle inconsistencies that refused to resolve themselves. Buildings appearing in their earliest photographs already complete in proportion and system integration. Infrastructure referenced in reports as fully operational without documentation of its developmental stages. Engineering language that assumed prior knowledge but never explained its origin. It wasn't what was present that unsettled me. It was what was absent. No crude early versions, no visible experimentation, no documented learning curve preceding mastery. Instead, mature systems appearing without transition. The 19th century is described as an age of invention, built through incremental refinement. Yet, the structures that remain suggest deployment rather than experimentation, coordination rather than improvisation, not scattered growth, not isolated advancement, but synchronized execution. That is where the unease begins, not with a declaration that something forgotten existed, but with a simpler and far more measurable problem: coordination without communication. How did complex, standardized systems emerge across continents in an era defined by slow transport and limited information exchange? Once you begin asking that question, the archival silence becomes impossible to ignore. And once you see the pattern, you can't unsee it. The debate almost always begins in the wrong place. Did Tartaria exist? Was there a hidden empire erased from official maps? Those questions demand a yes or no answer too quickly, and once we move into conclusions, the investigation stops. I found myself asking something different. Not whether a lost civilization existed, but if the structures that remain were part of a larger integrated system, how would daily life inside that system have actually functioned? Because the evidence we can still measure is not mythological, it is infrastructural. Roads graded with consistent slope ratios across cities that never formally collaborated. Canal locks engineered with nearly identical dimensions in regions separated by language and politics. Railway systems emerging within decades of each other using compatible track standards and structural logic before international engineering bodies were fully established. This creates a coordination problem. How were measurement systems aligned? How were construction tolerances maintained? How were architectural ratios repeated with such precision across continents in an era defined by slow mail, limited telegraph capacity, and no digital transmission of technical drawings? Not what's there, but what's missing. Where are the incompatible early attempts that should precede global uniformity? Where are the chaotic transitional phases before synchronization? Instead, we encounter mature systems appearing without learning curves. So the question shifts, not was there a lost empire, but how did synchronization occur? Coordination without communication becomes the central anomaly. And once you frame the problem that way, the 19th century no longer looks like isolated industrial growth. It begins to resemble a networked environment, operating at a level of integration we no longer fully understand. Imagine waking in one of these cities in the 1880s, not in a rural cottage, not in a crude timber dwelling, but inside an apartment building whose ceilings rise 14 or even 16 feet above the floor. That detail alone deserves attention. Heating efficiency in the 19th century was limited. Fuel was expensive. High ceilings waste heat. Yet across Paris, Vienna, St. Petersburg, New York, Buenos Aires, the same vertical proportions repeat with almost mathematical consistency. The windows are equally striking. Tall, narrow, extending nearly from floor to ceiling, often aligned vertically across entire facades. This is not random ornament. It is standardized geometry. The spacing between windows mirrors structural load intervals. The ratios remain consistent across blocks, districts, even continents. Pattern books can explain stylistic spread. They cannot fully explain structural uniformity embedded into masonry tolerances and foundation widths. Morning light enters deliberately. Solar orientation appears calculated. Corner buildings maximize seasonal angles. Courtyards function not only as aesthetic features, but as light wells and ventilation regulators. Air circulation systems are integrated into wall cavities far larger than simple plumbing would require. Natural convection appears engineered rather than accidental. The ornamentation raises further questions. Crown moldings carved with extraordinary precision, plaster relief repeating identical motifs across cities separated by oceans, geometric patterns embedded into cornices, friezes, and archways, all supposedly built by independent contractors working with limited communication. How do identical proportional systems emerge under those conditions? Then there is scale. Doorways exceeding practical human necessity, staircases with unusually deep treads, hallways wide enough to accommodate flows of movement that seem excessive for residential density, ceilings gradually decreasing in height on upper floors, suggesting intentional pressure or ventilation gradients rather than arbitrary design. Why construct at this scale? Official history calls it grandeur, civic pride, architectural fashion. But fashion does not require engineering redundancy. Fashion does not demand load-bearing precision that modern restoration teams struggle to replicate economically. These buildings were not fragile experiments. They were mature implementations, not primitive, not transitional, but complete. Step outside onto the street. The paving is graded with consistent slope ratios to manage runoff. Drainage systems connect seamlessly to underground sewer networks, extending for miles. Many of these networks still function today. Brick vaulting beneath the streets demonstrates uniform curvature. The tolerances remain tight even after more than a century of subsidence. Again, the same problem emerges. Mature systems appearing without learning curves. The 19th century is described as an age of experimentation. Yet the physical environment suggests deployment at scale. Entire districts rising within decades, already synchronized with transport, water distribution, and waste management systems that integrate cleanly with surrounding infrastructure. Not what's there, but what's missing. Where are the crude early versions? Where are the incompatible prototypes before standardization? Instead, we wake in a city that feels already coordinated, already measured, already aligned. And that is where the question deepens. If daily life operated within such precision, who maintained the standards? Who synchronized the ratios? Who ensured compatibility across regions before modern regulatory institutions existed? Coordination without communication. Once you see it, you can't unsee it. If this line of investigation resonates with you, consider subscribing or becoming a member. This research requires time in archives few people visit, examining documents most historians overlook. Your support allows these questions to be pursued carefully, methodically, and without predetermined conclusions. Step further into the city and the streets begin to present their own anomaly. They are not narrow medieval lanes gradually widened over centuries of incremental use. Many are remarkably broad, often far exceeding what simple horse-drawn carriage traffic would require. Boulevards extend in straight, uninterrupted lines for miles, intersecting at precise angles, frequently aligned with cardinal directions. North-south, east-west. The repetition is not occasional. It is systemic, appearing in city after city across Europe, North America, South America, and parts of Asia. Official history attributes this to 19th century modernization movements, urban reform, sanitation improvement, fire prevention, visionary planners imposing order onto chaotic settlements. But when you examine the timelines closely, entire districts appear already aligned before the major reforms supposedly took place. In several cases, the grid structure predates the population density that would have justified such expansive thoroughfares in the first place. From elevated perspectives, the patterns become even more difficult to dismiss. Radial designs converging on centralized nodes, star-shaped fortifications visible across multiple nations, constructed with nearly identical geometric logic, circular plazas from which evenly spaced avenues radiate outward with measured precision. These are not organic growth patterns shaped by accident or convenience. They are calculated layouts embedded into the land itself. The grading of these streets adds another measurable layer. Even in cities with challenging terrain, slopes are controlled with striking consistency. Drainage channels are embedded at predictable intervals. Stormwater systems connect to underground networks, extending for miles beneath the surface. Many of these brick-lined sewer vaults still function today. Their curvature remains intact. Their gradient still operates within efficient flow tolerances after more than a century of subsidence and urban pressure. Not improvised solutions, not crude transitional experiments, but durable, standardized engineering implemented at scale. And again, the global pattern emerges. Paris restructures under Haussmann. Chicago rebuilds after the fire. Buenos Aires expands rapidly. St. Petersburg formalizes monumental avenues. Washington, D.C. overlays diagonal axes onto an orthogonal grid. Different political systems, different economic structures, different surveying teams. Yet the geometric principles converge toward the same structural logic and proportional ratios. Where are the incompatible models that should precede uniformity? Where are the failed drainage systems, the misaligned grids, the chaotic experimental phases that naturally accompany urban evolution? Instead, mature systems appear almost simultaneously. Not what's there, but what's missing. The streets imply centralized surveying capacity, standardized measurement protocols, and synchronized execution across enormous geographic distances, all during a period defined by slow correspondence and limited technical exchange. Coordination without communication. Walk these streets with that question in mind, and the geometry stops feeling incidental. It feels intentional, measured, executed with a level of synchronization that the official narrative does not fully account for. And once you see that alignment, you can't unsee it. If the streets were measured and aligned, the movement upon them introduces a second layer of complexity. By the 1860s and 1870s, urban photographs begin showing organized traffic systems that appear far more integrated than the primitive narrative suggests. Street railways operating on fixed tracks, cable car systems requiring underground machinery and centralized power distribution, elevated trains appearing in major cities within remarkably close time frames. New York installs elevated rail in the 1870s. Chicago follows. Berlin expands tram systems. Budapest electrifies transit before the end of the century. San Francisco implements cable propulsion requiring continuous mechanical coordination beneath the pavement. These systems are not isolated experiments. They require surveying precision, synchronized scheduling, standardized track gauges, maintenance depots, and power transmission infrastructure. And they appear quickly. Where is the prolonged period of incompatible gauges and chaotic trial networks that one would expect in a fragmented industrial world? Instead, transit systems across continents adopt compatible engineering logic with minimal visible developmental confusion. The hardware differs in material detail, but the structural principles align. Streetcars follow predictable corridors already embedded into the urban grid. Depots connect seamlessly with rail yards. Elevated platforms integrate into surrounding architecture with load tolerances that imply prior planning. These are not temporary improvisations layered onto medieval streets. They feel anticipated. The coordination problem deepens. Who standardized the dimensions? Who ensured compatibility of rolling stock, rail width, signaling conventions, and electrical adaptation across countries that were often political rivals? Telegraph lines existed, yes, but telegraph does not transmit mechanical drawings or harmonize engineering culture overnight. Again, mature systems appearing without learning curves, and then another pattern emerges. After 1900, something changes. The rapid synchronization slows. Technical fragmentation increases. Competing standards proliferate rather than converge. Why does coordination peak in the late 19th century and then destabilize? Not what's there, but what's missing. Urban transit suggests a level of shared technical vocabulary that implies institutional integration beyond what official accounts describe. Coordination without communication becomes increasingly difficult to ignore. Once you see the simultaneity, you can't unsee it. If movement on land appears coordinated, movement on water reveals something even more difficult to reconcile. Throughout the 18th and 19th centuries, canal systems expanded at extraordinary speed across multiple continents. The official narrative frames this as the triumph of industrial engineering, incremental, ambitious, often experimental. But when you examine the physical structures that remain, a different pattern emerges. Lock systems in Britain operate on standardized chamber dimensions within decades of their initial construction. The British canal network reaches roughly 4,000 miles of navigable waterways in approximately 60 years, not gradually refined across centuries, but implemented rapidly with compatible lock widths, consistent grading, and water management protocols that align across regions built by supposedly independent companies. In the Netherlands, canal networks demonstrate precise hydraulic calibration, water levels maintained through coordinated sluice systems, pumping stations lifting water uphill long before electric grids were widespread. In Belgium and northern France, interconnected waterways share standardized dimensions that imply unified surveying practices. These are not improvised rural ditches, they are engineered corridors. Then there is the Grand Canal in China, over 1,000 miles long, connecting river systems across vast geography, operating with lock systems and seasonal water regulation centuries before European industrial expansion. The scale alone challenges assumptions about decentralized development. Across Europe, Asia, and North America, canal infrastructure shares recognizable engineering logic. Grading tolerances remain remarkably consistent. Reservoir placement suggests predictive hydrological modeling. Lock chambers operate with proportional ratios that appear mathematically optimized rather than experimentally derived. Where is the learning curve? Where are the decades of incompatible lock dimensions, collapsed embankments, hydraulic failures that typically precede refinement? Instead, mature systems appear early in their documented history. Maintenance records discuss operation rather than experimentation. Not what's there, but what's missing. The coordination required to maintain water levels across hundreds of miles is substantial. Locks must operate in sequence. Reservoir release must synchronize with downstream flow. Embankments must be reinforced according to shared standards. This is systems engineering, not isolated craftsmanship. And once again, the timeline compresses. Canal networks across Britain expand rapidly in the late 18th century. Continental Europe follows with compatible designs. North American canals emerge with similar structural principles, all before global engineering conferences and standardized international codes formally existed. How were hydraulic calculations shared? How did surveying accuracy achieve compatibility across political boundaries? How were tolerances maintained without centralized oversight? Coordination without communication. By the late 19th century, rail begins replacing canals. Many waterways are abandoned. Pumping stations fall silent. Technical journals shift focus. After 1900, something changes. Hydraulic discourse becomes fragmented, specialized, narrower. The integrated water systems remain physically visible, but the conceptual framework that unified them fades. And once you see that disappearance, you can't unsee it. If waterways reveal coordination, overland trade networks extend the pattern even further. The Silk Road is often described as a loose collection of merchant trails, caravans moving slowly across deserts and mountain passes with minimal organization. But when you examine the physical infrastructure that supported those routes, the story becomes more structured. Caravanserai appear at remarkably regular intervals across Persia, Central Asia, Anatolia, and parts of North Africa. Large enclosed courtyards capable of housing hundreds of travelers and animals. Thick perimeter walls. Standardized layouts. Water systems integrated into arid landscapes. Storage chambers positioned with logistical logic rather than decorative intent. These were not random ends. They were nodes. The spacing between many of these stations corresponds closely to the daily travel limits of pack animals. Not approximated, calibrated, across territories governed by different empires, speaking different languages, operating under different currencies. And trade itself reflects synchronization. Silk from China reaching Mediterranean ports with predictable regularity. Spices from India appearing in European markets within coordinated cycles. Contracts written in one jurisdiction honored in another. Bills of exchange functioning across political borders long before instantaneous communication. How? How were price signals transmitted? How were currency exchange rates stabilized across thousands of miles? How were disputes resolved without centralized global arbitration? Telegraph would later accelerate communication, but much of this coordination predates its widespread adoption. Not what's there, but what's missing. Where are the chaotic breakdowns that should accompany such vast decentralized exchange? Instead, we see systems that appear integrated, coordination without communication. The caravan routes, like the canals and boulevards, suggest institutional memory and standardized protocol that transcend local governance. And yet, the documentation explaining how that synchronization operated remains thin. Once you see the structural regularity, the image of isolated, primitive trade corridors begins to dissolve. This is where historians usually stop listening, because once aerial transport enters the discussion, the discomfort increases, not because powered flight is controversial, but because of timing. Throughout the mid to late 1800s, patent records document dirigibles, lighter than aircraft, propulsion experiments, and gas production systems. Newspapers describe aerial exhibitions. World's fairs showcase tethered balloons carrying passengers above exposition grounds. None of that is disputed. What becomes more difficult to reconcile is the scale and distribution of experimentation. Reports appear in Europe, North America, Russia, and parts of Asia within a relatively compressed time frame. Engineering journals reference lift capacity, stabilization methods, and mooring systems. Rooftop masts appear on prominent civic buildings. Elevated anchoring points are integrated into architectural plans. I'm not claiming fleets of commercial airships crossing continents daily. There is no need for exaggeration. Even limited deployment changes the equation. Even small-scale operational use implies reconnaissance capability, rapid elite transport, and information transfer faster than overland routes would allow. And then after 1900, something changes. The references thin out. Patent enthusiasm diminishes. Aerial experimentation becomes reframed narrowly around military and spectacle contexts. The architectural mooring points remain in some cities, but their function fades from documentation. Why? If the technology was progressing, why does the narrative fragment? Why does discussion of lighter-than-air systems retreat just as other industrial systems supposedly accelerate? Not what's there, but what's missing. Coordination without communication becomes slightly more plausible if even limited aerial transport existed. Yet mainstream historical narratives treat such possibilities as marginal footnotes rather than infrastructural considerations. And once you notice the abrupt shift in documentation after 1900, you can't unsee it. If the exterior geometry raises questions, the interior spaces deepen them. Basements in many 19th century buildings extend far deeper than simple storage would require. Multi-level underground chambers with brick vaulting, sealed rooms with pressure-resistant walls, corridors connecting to adjacent structures without appearing on official plans. In renovation projects today, contractors routinely uncover rooms that do not match the documented footprint of the building above. Official explanations label them as cellars, coal storage, or foundation reinforcement. Sometimes that is accurate, but not always. Some chambers are too large for fuel storage, too structurally refined for temporary use. Walls lined with mounting points whose function is unclear. Pipe connections leading to sealed conduits that terminate in unknown directions. Ventilation shafts that extend vertically through multiple stories, far exceeding the needs of simple heating systems. On upper floors, the pattern continues. Ceiling heights gradually decrease as elevation increases, suggesting intentional airflow gradients. Central atriums covered by glass roofs function as light wells, but their framing tolerances suggest additional structural purpose. Rooftop platforms with reinforced load distribution appear in buildings where no documented equipment required that capacity. In certain cases, rooftop elements align with astronomical angles. Whether symbolic or functional remains debated. But the recurrence across cities is measurable. Not random ornament, not isolated curiosity, but repetition. Not what's there, but what's missing. Where are the installation manuals for these integrated systems? Where are the engineering journals explaining the full function of these interconnected spaces? Instead, documentation describes aesthetic form while leaving operational integration unaddressed. The buildings feel like shells whose internal logic we partially recognize but no longer fully understand. Mature systems appearing without learning curves. Once you begin examining the interiors with that framework, the absence of explanation becomes as visible as the architecture itself. If civic buildings, streets, and canals suggest coordination, the factories intensify the problem. By the 1830s, textile mills in New England were already operating at massive scale. Photographs and engravings show floor-to-ceiling machinery arranged in disciplined rows, rotating shafts, transferring mechanical energy across entire halls, belting systems synchronized with remarkable precision. This is not a small workshop, gradually experimenting with new tools. It is integrated industrial deployment. By the 1850s and 1860s, steel foundries in Britain and Germany were producing at volumes requiring consistent metallurgical control. Ceramic works in England, glass factories in Bohemia, chemical plants in France, all appearing within a relatively compressed time frame. Industrial capacity does not slowly inch forward in the physical record. It seems to arrive organized. The official narrative calls this the Industrial Revolution, incremental innovation, trial and error, competing inventors refining techniques over decades. But where are the long phases of incompatible machinery? Where are the chaotic transitional systems that should precede synchronization? Instead, we encounter mature systems appearing without learning curves. Precision metalworking equipment capable of producing interchangeable parts appears earlier than many assume. Components manufactured in one region fit into assemblies constructed in another. Hydraulic presses operate at pressures that imply deep material science knowledge. Electrical generation equipment emerges in multiple countries before the narrative consolidates around a handful of famous names. Systems deployed, not invented. Inside these factories, labor organization reflects similar integration. Hundreds of workers operating complex machinery with coordinated timing. Power distribution arranged through centralized mechanical networks. Standardized gauges and fittings appearing across industries that supposedly developed independently. Training at this scale would require institutional structure. Measurement protocols would require agreement. Calibration standards would require communication. Yet documentation of how this synchronization was achieved remains fragmented. We have records of patents and celebrated inventors, but far fewer records explaining how thousands of facilities adopted compatible tolerances across borders within decades. Not what's there, but what's missing. Where are the incompatible bolts and mismatched shafts that should mark decentralized development? Where are the prolonged failures before standardization emerges? Instead, compatibility appears quickly. Coordination without communication. Then, after 1900, fragmentation increases. Competing electrical systems, divergent industrial standards, patent disputes intensify. The integrated tone of late 19th century engineering discourse begins to narrow into specialized silos. Why does the period between roughly 1850 and 1900 appear unusually synchronized? Once you see that compression of industrial maturity without visible developmental scaffolding, you can't unsee it. And the pattern continues beyond the factory walls. If factories reveal industrial coordination, the markets reveal financial synchronization at an equally complex level. By the mid-1800s, commodity pricing demonstrates remarkable consistency across continents. Grain prices in Europe respond to harvest yields in North America. Cotton harvested in the American South moves, predictably, to mills in Manchester. Tea shipped from China arrives in London within structured trade cycles that imply scheduling precision rather than sporadic exchange. This was not barter. This was integrated commerce. Bills of exchange circulate across empires. Letters of credit are honored in distant ports. Insurance contracts cover shipments traveling thousands of miles through multiple jurisdictions. Arbitration mechanisms function across linguistic and political boundaries, all before instantaneous electronic communication became universal. How were price signals transmitted so reliably? Telegraph existed, yes, but global telegraph coverage was incomplete for much of this period. And telegraph does not explain standardized accounting practices or synchronized currency exchange frameworks emerging almost simultaneously in different financial centers. Not what's there, but what's missing. Where are the systemic collapses that should accompany decentralized global trade? Where are the extended periods of incompatible currency regimes disrupting exchange? Instead, the late 19th century often shows coordinated commodity movements, predictable arbitrage patterns, and integrated financial instruments functioning with surprising stability. Market buildings themselves reflect this structure. Large exchange halls engineered with climate regulation, storage facilities calibrated for specific goods, administrative offices embedded into architectural complexes that imply bureaucratic oversight operating at scale. Coordination without communication. And then again, after 1900, something shifts. Financial volatility increases. Competing national standards intensify. Institutions formalize and centralize authority that previously appears more diffuse. If integrated commerce operated at such scale before modern digital networks, what institutional scaffolding supported it? Once you begin tracing trade flows as infrastructure rather than abstraction, the synchronization becomes difficult to ignore. If markets were synchronized, some coordinating structure must have existed behind them. Throughout the 19th century, trade guilds, professional societies, fraternal orders, engineering associations, and standards committees proliferated across continents. Many maintained international correspondence long before centralized global governance formally emerged. Architects shared proportional systems. Engineers referenced common calculation methods. Surveyors adopted compatible measurement logic, even when political borders separated them. These organizations rarely dominate mainstream historical narratives. They appear in footnotes, membership lists, archive proceedings, yet their influence is visible in the uniformity of outcomes, identical building codes appearing in different nations, standardized rail gauges spreading rapidly, shared technical vocabulary emerging in journals across languages, certification systems validating expertise beyond local jurisdictions, parallel authority structures, not replacing official governments but operating alongside them, establishing norms, disseminating technical knowledge, and harmonizing practices in ways that suggest institutional continuity. Not what's there, but what's missing. Where are the records of prolonged disagreement before consensus? Where are the fractured standards persisting for decades? Instead, alignment appears relatively quickly. Coordination without communication becomes less mysterious if such bodies acted as silent integrators. But documentation of their internal mechanisms often remains sparse. And that absence raises another question. How much of the synchronization we attribute to spontaneous progress was in fact maintained by structures we no longer fully examine? The World's Fairs offer a concentrated glimpse of this synchronization. The Crystal Palace in 1851, the Paris Exposition of 1889, the Chicago Columbian Exposition of 1893. Massive international exhibitions constructed within astonishingly short time frames. Hundreds of buildings, acres of coordinated design, participation from dozens of nations. These events required global logistical planning years in advance. Architectural harmonization, material transport, standardized measurement systems, electrical integration, water supply, waste management, crowd control, all executed with a level of coherence that implies institutional depth. And yet, many of the structures were described as temporary. Temporary buildings engineered with permanent precision, vast glass halls assembled rapidly, then dismantled, monumental facades constructed, displayed, and removed, architectural elements appearing fully mature, not experimental. Where did the expertise originate? Where did it go? Not what's there, but what's missing. The exhibitions demonstrate organizational capacity that challenges the idea of fragmented 19th century society struggling toward modernity. They suggest the existence of shared technical vocabulary and coordinated execution across continents. After 1900, something changes. The scale shifts. The architectural language fragments. Integration narrows into specialized disciplines. Why does the late 19th century appear uniquely capable of synchronized global spectacle? Once you see the compression of maturity and coordination in these events, you can't unsee it. Beyond spectacle and industry, the most revealing systems are the ones embedded into daily domestic life. By the mid to late 1800s, major cities operated gas distribution networks, extending for miles beneath their streets. Underground pipes carried combustible gas safely into thousands of buildings. Pressure had to be regulated, leaks had to be prevented, flow had to remain stable across seasonal variation. This is not trivial engineering. Water systems were equally complex. Reservoirs constructed at elevation, aqueducts spanning long distances, filtration facilities employing chemical processes, pressurized distribution, delivering running water into multi-story buildings decades before electric pumping became standard. Street lighting networks appeared in organized grids, not isolated oil lamps, but centralized systems feeding rows of fixtures aligned along boulevards. Maintenance schedules implied administrative oversight. Replacement components were standardized. These were mature civic utilities, not experimental prototypes. Not what's there, but what's missing. Where are the decades of chaotic trial systems before reliability? Where are the incompatible pipe fittings and unstable pressure gradients that should accompany early infrastructure? Instead, many cities display fully operational networks within surprisingly compressed timeframes. Coordination without communication. And then, after 1900, fragmentation increases. Competing electrical standards replace gas. Municipal systems become localized and politically entangled. The earlier impression of synchronized rollout gives way to jurisdictional complexity. If everyday households depended on such integrated infrastructure, the knowledge supporting it must have been equally integrated. And that brings us to the final question.